Hello and welcome to our final lesson of chapter 1, which is a review of exponential functions and then also an introduction to a specific base using exponential functions. This is meant to be just a review and an introduction. Most of this stuff will be used much later in the course towards the end of chapter 3. An exponential function, a reminder, is of the form f of x equals a times b to the power of x, where b is the base, which is a constant. Your exponential laws, again, we refreshed these when we did radicals last chapter, so you can take a look at those if you need. Also, a reminder that if you have a minus b squared, this is not equal to a squared minus b squared. A minus b squared is equal to a minus b times a minus b, which is equal to a squared minus 2ab plus b squared. If you are adding or subtracting inside of the brackets, you cannot just distribute the exponent. You must FOIL, okay? So we'll just do a quick refresher of how to graph these things. You may make yourself a table of values if you would like. So if I make a table of values here, if I pick, say, x is -3, this is 2 to the power of -3, which is 1 over 8. If I pick -2, this is 2 to the -2, which is 1 over 4. -1 would be 2 to the -1, which is 1 over 2. An exponent of 0 would be 2 to the 0, which is equal to 1. An exponent of 1 would be 2 to the 1, which is just equal to 2. An exponent of 2 would be 2 to the 2, which is equal to 4. An exponent of 3 would be 2 to the 3, which is equal to 8. If I want to draw this, we can see the easiest point to start at would be 0, 1. And then we also have a point at x is 1, y is 2, x is 2, y is 4, x is 3, y is 5, 6, 7, 8. Maybe a half would be okay, but the other ones are going to be very hard to do. You can see that no matter what the x exponent is, there's no way we're going to get down to a y value of 0. We actually have an asymptote here. At y equals 0. And now this makes it a little easier for me to connect my points. Okay, our domain for any exponential function that is basic like this, our domain is all real numbers and our range is all real numbers. Or sorry, our range is greater than 0. Okay, and we have a y-intercept at 0, 1, and there is no x-intercept because of our asymptote and our domain. So this will be true for any basic exponential graph where you have some base to the power of x. As soon as you do any transformations, you must consider those for all of these features as well. The asymptote, domain, range, and intercept can be altered by transformations depending on what that transformation is. Okay? So there's a new base that we're going to look at today, which is called the natural base e. So a function, exponential function, f of x equals e to the x is the most frequently occurring function in calculus, is one of the most frequently occurring function in calculus, and its applications. All it is an exponential function with a base e. E is this constant here. The pattern does not keep repeating. You even have an E button on your calculator. It is an increasing function because e is bigger than 1, and it is continuous. It has the same domain, all real numbers, and the same range, y is greater than 0. It looks like this below. It has this same y-intercept here. Okay, and we have an asymptote along the x-axis. Okay. Now, a little feature about our natural base e is that normally when we look at logs, okay, a couple of reminders. When we look at logs, usually we have something like log base 10 of 100, and this would equal to 2 because we have 10 to the power of 2 equals 100. So for any logarithm, log base a of b equals c, this corresponds to some exponential a to the power of c equals b. Okay. If we had log base 10 of 10, this would equal 1. And we could also just write this as log 10 equals 1. So a reminder, if no base is declared, we assume it is 10. Okay. Now we have, what if we did e here? What if we had a log with a base of e? So if I did log base e of e, this would also equal 1. Okay. Now, because e is so common, we actually have a special log that we use, and it's indicated by ln. It's called the natural logarithm because it goes with our natural base. And the same thing, you have an ln or a ln button on your calculator. Okay. So log base e of some value x is the same thing as writing ln x. Okay. If I did log base e of e, this is the same thing as writing ln of e, which is equal to 1. So you are going to be seeing ln quite a bit later in the course. All ln is a log with base e. All e is this gross decimal number from the previous page. Okay, it's just a number. E is just a number. It doesn't need to be scary. Okay, so for example, if I want to determine the domain and range of this, the first thing I would do is I would rewrite this as 1 over e to the x times 1 minus x. Okay. So if I want to find the domain of this, I know that the denominator cannot be 0, which means e to the x can't be 0, which is already the case. This is already the case for 1 minus x cannot be 0. So if 1 minus x can't be 0, that means x can't equal 1. This is already true. E to the x is always greater than 0, as we saw on the previous page. All of these y values are positive. Okay? We already have a range of y is greater than 0. Okay? We already have that. So there's our domain. Okay? Now, since we already know that e to the x is greater than 0, right? If e to the x is greater than 0, we need to consider, okay, so what's going to happen here when 1 is equal to x? So we know that when y is greater than 1, if x is greater than 1, then when you multiply these together, you're going to get a value greater than 1. If x is less than 1 here, then we know that you're going to get a negative value. Okay. Now, the easiest way to find the range for this would be to graph this thing. So let's pull up a new Desmos window here, and let's graph this. I would never ask you for range of something like that on a test if you didn't have access to a graphing software of some sort, just as a heads up. Okay, so this is what it looks like. So you can see you've got two pieces. Your one piece on the left, your minimum value is y is 1. So this piece on the left here is y must be greater than or equal to 1. And on the right, you can see that this thing, it looks like it's at 0, but if you zoom in, you'll see that it's not. It's approaching 0. Okay. So we've got two pieces here. One piece for your range was that y had to be greater than or equal to 1, and your other piece was y is less than 0. Okay? Graph to see this easily. Okay? All right, so let's try an applied question for these. All right. So we have from math 12, we looked at exponential functions and how to solve these. So when you looked at these, you looked at mostly growth or decay using the formula, and please don't write this down just because I'm going to erase it in a moment, using the formula y equals y naught 1 plus r to the power of t or 1 minus r to the power of t, right? Or you might have used C here for initial and an A here for final. There were a bunch of different ways of doing this, but basically the number in front of the brackets was your starting value. Your R was your growth or your decay rate, and your T was time. Now, what E is it tells us about exponential growth specifically. And I will put up a PDF that goes through and explains why it works and how it is um, the number it is and how it was found. Basically, it was found experimentally, but you can go through and take a look at that if you are interested in why this is true. But essentially, we have a new exponential growth formula that we are going to be using, and we will be using it later in the year as well. So y equals c e to the k t is going to be your new exponential growth or decay formula that you are going to be using for most of this course. Okay. C is your initial value. T is your unit of time. Okay. K is your growth constant. And Y is going to be your final value at the given time T. Okay. So this is going to be something that you are going to see later in the course quite a bit, okay? Especially if you're doing the AP portion. All right. So let's try this question. So we've got a researcher placed 100 bacteria into a dish at time t equals 0. So this tells us that C is equal to 100. Okay. Now it says that she discovered 7 hours later, the culture grew to 625. So at t equals 7, y equals 625. Okay. It says assuming exponential growth. So this means we can use y equals ce to the kt. What is the growth constant k? So we're trying to find k. All right, so let's try this. So we've got y equals ce to the kt. We know that c is 100. We're trying to find k. We don't know that. T is 7, and y is 625. All right, so now the problem we have here is that we need to find k, which is a missing exponent. We need to isolate k. So in order to do that, we know from Math 12, in order to bring an exponent down, we can log both sides of an equation. Before we log both sides, you're going to want to move the 100 over. So if I divide both sides by 100, I get 6.25 equals e to the 7k. Now, instead of logging both sides, I'm going to ln both sides using ln, our natural logarithm, because of the base e. If this was a 10, I would want to log using base 10. If this was a base of 2, I would want to log using base 2. It would be the quickest and most efficient way to solve for a nice, neat answer. All right. So if I ln both sides, That's going to allow me to bring the 7k down in front on the right. And because I logged using the same base as the base of my exponential, you did that on purpose so that that would equal 1. So ln e is equal to 1. Remember, that's just the same as log base e of e from up here. Okay, these are going to come in handy. All right. Now, once I do that, I'm trying to get k by itself, so I would divide both sides by a k. And we can leave it here, or we can plug it into our calculator, and we would get a lot of decimal places, but to 2 decimal places, this would be about 2/6. So depending on the question will depend on how you want to leave your answer. So this is your approximate answer, which the question said was fine, round to 2 decimal places. And this would be your exact answer. So if we had to continue on in the question, then we would want to keep as many decimal places as possible or use the exact answer. So in your board questions today, you will see questions like that where they're going to give you this information, but then they might say, okay, so find how many bacteria there were after 7 hours. Well, I don't have K, so I cannot find that information until I know K. So a lot of the times the question is almost a two-part question. They give you enough information to find your K, which you can then use to find the actual piece of information you want. Okay? And that's all for today.